Hello, welcome to the lecture on cell balancing in my Battery Management Systems course. This lecture was largely recorded along the gorgeous Washington State coastline just south of Anacortes, where I stayed for 4 days trying to get this lecture done. Thank you for joining me in the transition to sustainable energy. Balancing is a complex topic with direct impacts on how the user experiences the end application. So I've split this lecture into several videos with different target audiences. In this first video, I'll explain what imbalance is and the mechanisms that cause imbalance. The next video presents some specific application examples and impacts, and I tried to make it accessible to a wide audience. In the next video, we'll quantify the total amount of imbalance we might need to compensate for. The next video covers thermal design, an important topic for the electrical and mechanical engineers actually designing the BMS PCB and incorporating it into a battery pack. The next video considers when to balance, an important topic for the firmware engineers writing the control software and also for system engineers. The last video covers active balancing. This is the introduction video in the cell balancing lecture. First, let's describe what balancing does. Imagine an imbalanced battery pack, schematically shown on the left. One cell is fully charged, and two cells are at lower states of charge. Because one cell is at top of charge, we cannot charge the pack anymore. When we discharge that imbalanced pack, the lowest cell limits discharge. So in practice, the imbalance reduces that battery pack's usable capacity. In this example, with 33% imbalance, the imbalanced pack can source 2/3 of the amp hours that would be available if the pack were balanced. Balancing, roughly speaking, puts all the cells at the same state of charge. On the right, we have a balanced and fully charged battery pack on top, and a fully balanced and discharged pack on the bottom. We are able to cycle a balanced battery pack through its full capacity to extract the maximum number of amp hours possible. The simplest and most common way to balance a battery pack is to selectively drain some cells by applying a resistor to them, like this. Resistors on the cells at higher state of charge discharge those cells to match the lowest cell. The result is a balanced battery pack with all the cells at the same state of charge. Let's look at balancing on a voltage versus state of charge curve. On the left, you see a plot of 3 cell curves as they might look in an imbalanced battery pack. Charging and discharging the battery pack is synonymous with moving left and right along all the curves. The voltages of the 3 cells are never quite equal. Balancing the battery pack means discharging individual cells. Rather than moving along the curves, balancing moves an individual curve itself. Passive balancing discharges cells, moving the corresponding curves left. Active balancing can move the curves either left or right. As you can see in the right figure, in a balanced battery pack consisting of cells with equal capacity and identical chemistry, the curves align. In most packs, cell capacities are not exactly equal, either due to manufacturing variations or due to unequal aging. Consider what balancing looks like with cells of unequal capacity. When the curves aren't identical, we can shift them left and right to align them at one point. If we pick that one point to be at top of charge, we have top balanced the pack. If we pick that one point to be at the bottom, that's bottom balancing. Or we can balance at some intermediate state. A more precise definition of balancing is that it equalizes either the voltage or the state of charge at one point on the operating range. Top balancing is in a sense ideal since it maximizes the total power we can extract from the battery pack. Since power is voltage times current, operating at a slightly higher voltage as with a top balanced pack provides slightly more power. Next, we'll discuss some processes that cause imbalance. Imbalance has a few causes. First, we have cell self-discharge. all cells very slowly lose charge over time. If you put a cell on the shelf and check it a year later, you will find the state of charge has decreased. If one cell self-discharges faster than another, they will become imbalanced. Self-discharge increases with temperature, so a temperature gradient across the battery pack will cause imbalance. Unequal loads also cause imbalance. For example, if the BMS utilizes multiple voltage sensing chips to measure the cell voltages, and if those chips draw slightly different currents, that difference will imbalance the cells powering one chip relative to the cells powering the other chip. Some internal defects or faults can cause high self-discharge in the affected cells, sometimes without propagating. For example, if you have a tiny defect in the separator, you might get a tiny local leakage between the two electrodes. Let's also talk about what doesn't cause imbalance. Capacity differences don't cause imbalance. I've heard this misconception repeatedly, so let's discuss it. Imagine two cells with unequal capacity. Here, I've drawn a factor of 2 capacity difference so we can see easily what happens. Let's start with both cells at 100% state of charge. As we discharge, the cell voltages deviate. When the smaller capacity cell is at 50%, the higher capacity cell is still at 75%. If all we look at is voltage, it appears that we have an imbalance. But when we charge again, the two cells reach top of charge concurrently. So in fact, this battery pack is balanced, top balanced to be precise. Let's show this on a voltage versus state of charge plot. Discharge the battery pack. When the yellow cell reaches empty, we must stop discharge. The green cell is still half full. The voltages of the two cells are quite different. Consider what this looks like with both curves on the same plot. In essence, the lower half of the green cell's capacity is unavailable. When the pack is fully discharged, it seems like we have an imbalance. But when we charge the battery pack, the cell voltages meet up again at the top. This is a top balanced pack. Differences in cell capacity cause the cell voltages to differ over some of the operating range, even though the battery pack is balanced. This is the end of the introduction video in the cell balancing lecture. Please continue with video 2.